Hi, this is Mrs. Murdock, and this is a post-lab discussion for the diffusion lab for AP Biology. So there were two graphs that come out of that lab that you're working on in class. And what you're doing is you're creating graph number 1 is from that dialysis tubing where you put different sucrose solutions into dialysis tubes and then you soak them in water for 30 minutes and then you got percent change in mass for each bag from that. So you have access to class data, and I want you to use the class data to create a graph of percent change in mass per sucrose molarity in the bags, right? So down along the bottom, your IV is the sucrose molarity inside the bags. And then your DV is the percent change in mass, or really the amount of water that flowed into the bags as a result of how much sugar there was inside them. So you remember when we discussed this before you actually did the experiment, the cups that had bags with increasing amounts of sugar inside the dialysis tubing bags, and all the cups just had tap water in them, right? So the solutions that the bags were soaking in were hypotonic to them. In fact, increasingly hypotonic, the more sugar was inside the bag, the more it caused the water to flow in, which is what a hypotonic solution does to a living cell. That the higher the gradient is, the more the difference is between what's outside the cell and what's inside, the more water has to flow in to try to reach equilibrium between the two solutions, right? The only solution that was a little different was the one where there was no sugar in the bag, right? The purple solution had 0 sugar. And so both the inside and outside of the bag were the same concentration. Therefore, that would have been isotonic, right? And most people still saw a little increase there, and that was probably because of the dye molecules that I put in that may have caused a little bit of water to flow. But that's okay. If you look at the trend in the data, I think it looks exactly like this. In fact, the data is really nice. And when you're inputting this graph into the assignment that I put on Schoology, you're going to need to put error bars on it, two SEMs, right? And this is not a good title, you know that. No, not a good title. You need to make sure that you come up with a title, and you can work with your friends on that today and help each other out. That's fine. And since we're using class data, with error bars, you're also going to need to add 2 things at the end. Your n value, or a sample size value, and just count up how many different teams did it. And the fact that you're using 2 values of the standard error, so 2 SEMs, so don't forget that. Okay, using a title that that uses the effect of the IV on the DV is perfectly fine here. Okay, you don't have to get any fancier than that. And what we're hoping is to see this exact trend in your claim. Remember that a claim, that's where you're going to describe the relationship between your IV and your DV. So your IV here is the sucrose molarity, the increasing sucrose molarity inside the bags. Your DV is the percent change in mass due to water flow, right, that happened as a result. So you need to write your claim based on the trend that you see, but also based on what the error bars are doing. So be careful of that. I'm not sure what they're doing right now. You're going to have to figure that out. And realize that even if you might get some error bars that overlap between 2 bars, but probably not between all of them. So consider that when you're writing your claim, okay? I'm going to go down to the next graph, which is the potato data graph. We can get this over here. Here we go. Okay, so the second graph is the potato soak graph, and I'm just going to need ink. Okay, so I'm just going to draw my axes in here. I check them out. There we go. All right. So this is going to be a line graph, and you are going to use all the class data, but you do not need to add error bars to this one. Okay, so no error bars needed. But I would like you to use as much data as we have to create the line. Okay, so you will give an n value whatever it is, but you don't need SEMs here, okay? And so also make sure in both graphs, make sure that you have changed the colors to the actual concentrations. So you're not, you know, your IV is not the colors. It's not the dye that made the water move. It's the actual concentrations. So 0, 0.2, 0.4. This should be along the bottom down here. 0.8. 1.0. There's your sucrose molarities. That is a 0, not a 6. Okay. All right, so when you plot this, what you're going to find is that it looks something like this. It's going to wind up looking like that. And what I want to do is explain what the different parts of the line above the 0 here and below the 0 really mean. So the cups that had potatoes in them that were at 0 and 0.2, in this instance, did those potatoes gain water or lose water? Gain water. Yeah, okay, so the potatoes that were up here, anything above that 0 line, the potatoes gained water. Because the solutions outside them, right? The solutions that were outside them were what to them? Yes, they were hypotonic. So everything above this line, all these points above this line represents solutions that would have been hypotonic to the potato and cause them to gain water, right? Okay. What about down here? These potatoes, what happened to them? Right, these potatoes lost water, and those of you who were superstars and actually came in and actually handled and looked at those potatoes in those different cups, you noticed that the potatoes that were in the 1.0 molar solution, that blue cup, they were all shriveled up. They really looked as though they had been dehydrated because that hypertonic solution around them had drawn the water out of them. And that's what happens to living cells in a hypertonic solution. So the solutions outside those potatoes, were hypertonic. So everything down here below that line, any of these solutions would have been hypertonic to the potato. So then what's this? That point right there. That's your isotonic point. That is the point that you use to determine the unknown sucrose concentration of those potatoes, which were a constant, but also a mystery, right? So we didn't know the concentration on the inside of the potatoes. We knew what was out here because we put it there, right? So maybe this was 0.6, and maybe those potatoes shrank and lost water in 0.6 due to whatever was inside them, right? So how do I use this graph then to determine this mystery sucrose concentration? You do something, you do something called interpolation. So you take a ruler, or your graph might actually make this really easy because it has lines on it. And you go down to intersect with the concentration that is the same as your isotonic point, where the potato neither gained or lost weight. That is the point where you know the potato concentration was the same as the solution it was sitting in. And even if we didn't have that particular solution made up, you can interpolate it wherever it happens to fall in the line. Okay? So now we have, from this graph, I don't know what it's going to be on the real graph, but this graph tells me that the inside of the potato is 0.4 molar sucrose. Now we know this. Okay, now what do we do with it? Well, we take it down and we're going to use it to calculate something totally different. We're going to calculate the water potential of the potato using that sucrose concentration, or that solute concentration, right? All right, so first of all, and if you haven't looked at it already, you can later, Mr. Anderson explains water potential really beautifully in the Ed puzzle I posted. So go look at that. And simply, water potential means it's a measure of the energy that water molecules have in a solution. And it depends on two things. It depends on the solute concentration, how much stuff is dissolved in it. The more stuff is dissolved in a solution, the lower the water potential is, because the water gets bound up with all those molecules that are in between and interfering with its movement. So the more solutes, the less water potential there is. Then there's also another factor, the pressure potential, which Mr. Anderson talks about. Now, since we did this experiment in an open cup at sea level with no, we didn't put it in an autoclave or anything, and we're also talking about the isotonic solution, we're going to assume that the pressure is 0. So you don't have to worry about this in your calculation. The solute potential has its own little equation, and this is on your formula sheet. You don't have to memorize it. It's right there, and you'll be allowed to use this on your paired essay, okay? It's negative I C R T. So let me take that apart for you. First of all, just pull out -1 as a factor, because solute potential is always going to be negative. If you add any solutes at all, it goes immediately negative. I is the ionization constant, and the ionization constant means when you put the solute into water, does it break apart or not? And sucrose doesn't. It stays in one piece. So we'll say this is 1, very simply. Since it's sucrose, it's 1. If it were NaCl, sodium chloride, then we would say 2. Because sodium chloride dissociates into 2 pieces. So that will be different. But this is sucrose, and all carbohydrates are just going to stay in one piece. Okay, C is what we just got from the graph. It's the molarity of the solute. So that I'm going to put in as 0.4. You will put in as whatever you get when you interpolate your graph. R is a constant that is in the formula sheet. It's always the same. Again, you don't have to memorize it. It's 0.0831, I believe. So you just plug and chug that. Okay? And T is temperature in degrees Kelvin. So those of you who've taken physics or chemistry may understand that. It's whatever the room temperature is in degrees Celsius. We're going to go with 21. Okay, and you can just use that when you use your calculations. 21 is usually about room temperature. Plus 273 degrees, which Lord Kelvin used because he figured out the temperature at which molecules don't move anymore, and that's a whole thing. But just to convert that, all you have to do is add those two numbers together, and you have your temperature in degrees Kelvin. So if you plug and chug this in a calculator, you'll get, I believe, -9.8. I'm just going to do this because I want to. And the units for water potential, right? So the potential of the potato is in bars, which is kind of a unit of pressure energy, right? So -9.8 is now your calculated water potential of the inside of the potato. And what we did to get that, there were 2 steps to that. We used the graph to figure out the sucrose molarity, which is your C value here. And then we input it there. And then we used the equation for solute potential, inputting the room temperature and all of the other things to get this value, which would be correct if this were the actual molarity of sucrose inside the potatoes. I don't think it is. I just made this up just to give you an example. So you'll have to figure out what the true C value is from your class data. Okay? All right, and that is all I'm going to say about the diffusion lab graphs and conclusions, and I hope that was helpful.